Hello and welcome. This is the Chapter 5 summary video. I was debating skipping this video, but some conversations with students have led me to the conclusion that some of you guys might still be struggling with some of the concepts out of Chapter 5, and you might need to see a few more examples. Hopefully this video provides you with a little bit more instruction to help you get through this particular chapter. So this is a figure we talked about in the chapter in terms of trying to understand changes in internal energy. And so some reactions will have energy absorbed. So the internal energy of the system, if you think of the energy itself, if we imagine going from A to B, some reactions will lead energy overall to being absorbed. And if that's the case, and we can imagine perhaps work and heat also have the same sign as delta E. So in this case, delta E is positive. And then we're seeing perhaps heat is being gained by the system, and perhaps work is being done on the system by the surroundings. Okay, now one thing confusing with this picture is this doesn't mean that a reaction that has a delta E greater than 0 necessarily has to have both of these quantities greater than 0. Q and W can be almost anything depending on how a particular reaction is carried out. And so, given that, the thing to kind of take away from this figure is just the idea that heating an object up is the same sort of idea as thinking about its energy going up. The same idea if a system, if you had almost like a piston that was pressing down on the reaction, that's the surroundings working on the system. That's what it means for W to be greater than 0. And the same thing here would be like a gas being absorbed into the reaction as well would allow you to predict that the W, given that change only, and assuming just only the consideration of the gas working on the reaction if it's being absorbed in, would allow you to predict that the W sign would be positive for that particular reaction. Now the opposite is the case where A to B is leading to the release of energy. So if we're thinking about the energy here, our delta E in this case is releasing energy. So energy is being released by the reaction into the surroundings. And so heat is flowing out of the reaction. So heat is lost by the reaction. So the Q of the reaction is negative here. And then the heat has to go somewhere. The heat is going to the surroundings. It's going to heat the surroundings up. So in this example, the temperature of the surroundings of the reaction should increase. In this example here, if heat is flowing into the reaction, the temperature of the surroundings should be dropping. Okay, and if we're ever touching the temperature or tracking the temperature of a reaction, we're really tracking the temperature of the surroundings of the reaction. So likewise, if you can imagine a reaction releasing energy, and the energy is being used to perhaps heat an object up, to give the heat to another substance, like the surroundings, you can also put the surroundings into motion. That would be accomplished with the work. Sort of the thermodynamic energy associated with putting objects into motion is described by work. So work is sort of related to a force times a distance. This is more of a physics construct. I think this is showing us that if we're going to be putting a relatively heavy object into some serious motion, that's going to take a lot of energy away from maybe going out of the reaction in the form of heat. So that if we see a reaction, we're looking at delta E is equal to the sum of Q plus W, that these can really be anything. The Q and W can be anything so long as they sum up to whatever the energy change is for the reaction. So delta E is a state function. Delta E is the same every time we carry a reaction out. If we flip the reaction, we flip the sign of delta E. And but the Q and W magnitudes and signs depend on how we're carrying the reaction out. Now we talk a fair bit in this class about chemical systems, where chemical systems aren't really going to be putting objects into any kind of serious motion. So the work term is either going to be pretty small overall compared to what the heat might be, what the heat changes that might be possible for a reaction. So the work itself ends up either being negligible or in some cases kind of canceling itself out. So we had the idea that delta H for a system at constant pressure was just equal to the heat change of the reaction at constant pressure. And then whenever we actually had a closed system, we were saying, well, delta H is approximately equal to QP. And this was what we are kind of using in our bomb calorimetry problems later on, is that even for a closed system, a closed container, we kind of have this approximation, the delta H is really pretty much approximately equal to the heat released by the reaction as if it were at constant pressure, with the idea being for a closed chemical system, work is just negligible for that particular system. So work is only sort of non-negligible, generally speaking, when you're putting some serious objects into some serious motions, and those become mechanical systems, not exactly a topic for discussion in a chemistry class. So reviewing the signs of Q, W, and E and their meaning, and this is always with the perspective of the reaction. So this is the Q of the reaction, this is the W of the reaction, this is the E of the reaction. You can also call it the system, the Q of the system, W of the system, the delta E of the system, not the surroundings. So whenever the Q of reaction is positive, that means that the system or the reaction is gaining heat. Okay, and when the sign is negative, means that the reaction is losing heat. So a Q reaction is just like a negative delta H, that the reaction is losing heat as the reaction takes place. Now the W being positive, if Q being positive means the reaction of the system is absorbing heat, if W is positive means the system or the reaction is absorbing work. So work is being done onto the system by the surroundings. So think of this meaning like a piston is being pressed downward onto the reaction. Now, if the reaction is doing the work, then it's moving the piston back upward, or it's pushing a gas out of the reaction. It's generating gas that is pushing the surroundings into motion. So that means that the work is being done by the system on the surroundings, just like if a system or a reaction is heating up a surroundings and the sign of Q is negative, the same thing. If a system is putting the surroundings into motion, then the sign of W is negative. And delta E being positive means that the system's gaining energy, and the delta E being negative means the energy of the system is being released. So that's easily thought of just energy diagram, positive going up, and then the negative going down. So let's review state functions again. So internal energy of a system is independent of the path by which the system achieved that state. And so certain functions are state functions, certain functions are not state functions. And so delta H and delta E are state functions. So the amount of energy or enthalpy a reaction must change in order for that reaction to occur is exactly the same if we repeat the reaction. It's exactly the opposite if we reverse the reaction. So this is just a simple idea. If you have A to B and your delta E is, say, 10 kJs uphill, you flip the reaction to go back to A, then you go back to it being minus 10 kJs. And if you go back to B, it takes another 10 kJs to go back up. You get another 10 kJs when you come back down. So this is working out every single time because delta E and delta H are path independent. Now, the key thing is that Q and W are path dependent. We've been saying this a bunch of times. Heat and W, the amount of heat, I think it's almost worthwhile to think of a exothermic reaction here, because I think it's an easy example to think of that particular type of reaction because it's releasing energy. So a combustion reaction is releasing energy when it occurs. The energy that's being released can either be used to give heat away to the surroundings or to put the surroundings into motion. And it's doing that by the reaction itself, losing heat, and then doing work on the surroundings. So the sign of Q of the reaction in that case would be negative, and the sign of W would be negative as well. Now the key is, you could be running that combustion reaction with the car in park, with the car in drive, with the car in first gear, second gear, third gear. You could be going uphill, downhill. So the amount of actual work that's being done onto the car is dependent on a lot of conditions. So you can get a variety amount of just heating up of the engine block versus amount of motion into the car, and it's just simply dependent on how that particular reaction is carried out. But you burn a gallon of octane fuel, you only have so much energy that you could possibly use to heat up the engine block or to put the car into motion. So the sum of the heat and the work change for a reaction is a constant dependent on the delta E, that state function for the reaction. So path independent, delta E, delta H, path independent, Q and W. So state functions here, heat and work, are not state functions. This example here is showing that a battery can be shorted out, or it can be maybe discharged by running a fan. The energy is the same. The battery has so much energy to give. It can either go into just heating up a coil, perhaps. Some of it could go into making the fan move. Maybe the fan heats up a little bit as well. but there's still only so much energy that that battery has to give off into heating up a substance or putting something into motion. So work can be, we can think of measuring perhaps, a reaction taking place here. The reaction, we have HCl, we have zinc that we can add to the pot. And so if we add zinc here, what can happen is zinc solid. Let me choose a different color. So zinc solid, let's do red. So if we have zinc solid, it can lose 2 electrons, become ionized, or can become oxidized, give up 2 electrons, and those electrons can be absorbed by the H plus ions, and the 2 H plus ions can absorb 2 electrons and form H2 gas. Now H2 gas forms and starts pushing this piston upward. Okay, so as the H2 gas is forming, because we're doing a reaction here where zinc solid is reacting with 2 HCl to form zinc chloride, AQ, HCl was an AQ, and then H2 gas forming, that this gas forming, we have a net gas being formed that's pushing away from the reaction. That's going to be the system doing work on the surroundings. It's going to do work on that piston by pressing it upward. So if you think of the reaction pressing the surroundings out of the way, then that means that the W sign of the reaction is negative for this particular reaction. Now there's this equation. I don't like to think of equations too much. One, because we don't usually have equations provided to us, and we see work is equal to negative P delta V. To me, it's just the thought is simple as doing work is a negative sign when the reaction's doing the work. When the reaction's pressing the surroundings out of the way by generating a gas to press the surroundings out of the way, then I can visualize or think that that means that work is being done by the reaction, and therefore it's negative. Okay, and so then if you imagine the opposite, if you imagine a gas is being consumed so the piston starts moving downward, then you could say for that reaction, then in that case, W would be greater than 0 if you have a gas being absorbed by the reaction. Okay, so the result of the zinc reaction here, gas being generated, the generated gas presses that piston out of the way. So enthalpy here, if a reaction takes place at constant pressure, i.e. in an open container, and the only work possible is this pressure volume work, we can account for heat flow during the process by measuring the enthalpy or just relating the enthalpy of the system. This is a quick derivation again to show this. I don't know if this is necessarily the most useful thing to see again, but enthalpy is just defined as the internal energy plus the PV, the pressure and the volume of the say gas. And so then if you talk about a reaction occurring where you can think of the change in enthalpy, the delta H, and then you could write the delta of both sides. So the change here is just implying the final minus the initial energy and the pressure volume of the system. You end up being able to write that delta H is then equal to delta E and then delta PV. But then if pressure is constant, then pressure is not changing. So if we have delta PV, let me write it this way. So if we have delta PV, then that would be equal to P delta V since the pressure is not changing. So the only thing changing in a constant pressure system might be the volume of the system. And so then there's a few things we might recall. If we do recall that work is negative PV, then maybe we can and we also remember that delta E is Q plus W. So we can substitute the Q plus W in for delta E, and then we can recognize that plus P delta V is the negative of work. So minus work is equal to plus P delta V. Okay, and so the plus P delta V is equal to minus W, and then there goes the work. Now, I think there's a fancier way of thinking of this derivation without doing the derivation, which is how can an open container system put the surroundings into motion when there's really nothing that it's pressing upon? Really not until you enclose a system with like a movable piston does the reaction become possible to actually put something into motion. So it's pretty hard to imagine moving an object when you don't have anything you're really pressing upon. So for a system in an open container, the issue would be that delta H is just equal to the Q. Now sometimes you see that little P symbol. I think it's actually slightly confusing because that P is just implying the heat change at constant pressure is equal to delta H. You could still say that delta H is equal to Q of the system. I like to call it Q reaction because you're saying delta H of a reaction is equal to the heat change of the reaction at constant pressure. Now, and then, like we've said a couple times before, once you actually close in, let's say you just have a closed container where there's no movable piston, it's just an enclosed reaction, so the pressure is no longer constant, now the volume's constant. What changes? Well, a lot actually changes, but what we end up doing is just summarizing when we get to the problems. Bomb calorimetry is the case where we seal a reaction up in a container. Then we have this delta H is then approximately equal to the heat change of the reaction. So we do a lot of, we expend personally a lot of energy to try to understand work. Then we get ourselves to a closed container bomb calorimetry problem where we could plug work in, figure it out, make a tiny little correction for the small pressure volume work being done inside the container, and then we just ignore it. So, I bring this up only to let you know that the book was discussing work, so we're trying to understand what's covered in our textbook. Use some of the practice quizzes and practice exams that you'll see to get a sense of the type of questions that you'll be responsible for. So the big things are really just trying to understand the cases where we can predict the sign of W, the sign of Q, the sign of delta E. Not every reaction you can predict these things, but some reactions you can. And sometimes it depends on how you're carrying the reaction out and some information you might know about the reaction. Like we did an example in class where you're told you're using a car burning gasoline and you know it's accelerating. In that case there, since you know the car is accelerating, it's being put into motion by that chemical reaction occurring. So you know that the chemical reaction is working on the car to put it into motion. So you know the sign of W has to be negative for the reaction being carried out in that case. And of course, a combustion reaction is releasing heat. So it's certainly causing the engine to heat up as it's taking place. There's going to be some heat being gained by the system. And we know combustion reactions should definitely be releasing energy. That's where we're getting the energy to put the car into motion. So it's an example of a reaction where we can kind of think of the signs of all three of those variables and understand what they mean for that particular system. So summary here for enthalpy. Enthalpy is an extensive property. So when we're looking at A to B versus in saying delta H is equal to, let's say, 25 kJs. If we cut this in half, have half A to half B, which is reasonable because that just means a half mole of A turning it into a half mole of B, that the delta H for that process should be cut in half. So it'd be a half times 25 kJs. The enthalpy change for a reaction is equal to the magnitude but opposite inside if you flip the reaction. So in this example, obviously B to A has a delta H of minus 25. That falls out from really just the first law of thermodynamics, that energy is neither created nor destroyed. If we went from A to B and back to A, and our delta H for that process, imagine we do like a Hess's Law little case of A to B and then B to A. And so there's no net change, so there's no reaction, so the A is canceling, B is canceling. If you add up your two delta H's, if you think of doing this like plus 25, delta H here is equal to minus 25, and so the delta H of our no reaction would of course be equal to 0, meaning that we're not creating energy by turning A into something and going back to A. If we were creating or destroying energy in this process, we'd be violating the first law of thermodynamics. So now the enthalpy change for a reaction depends on the states of the reactants and products. So whenever you see a delta H, sometimes we might say the enthalpy of combustion of a substance. Well, if you're talking enthalpy of combustion of, say, CH4, you often have to be told what the physical state is, in particular for water. So we're forming 2 moles of water, and it can be formed in the gaseous state or sometimes the liquid state. You'd have to know if you're given a delta H if water's in the liquid or the gaseous state. Now, CH4, room temperature is a gas, O2 is a gas, CO2 is a gas. We really don't have this issue with any substance other than water in this particular reaction. But the key for this example, if water is being formed as a gas or a liquid, water, gas, and liquid have a different enthalpy, and so therefore the reaction's delta H would depend on which physical state water's in. Now we can also predict that physical state, say, of water liquid to water gas. If you're going to vaporize liquid water, there's forces holding liquid water together. They have to be broken. So this delta H, we can definitely predict that this is endothermic. Enthalpy has to be absorbed by water for that reaction to occur. Likewise, if you have ice melting, that's also a case that the delta H can be predicted for all melting processes to be not exothermic, but endothermic, that the ice has to absorb heat to break the attractive forces holding the solid together. And then if you fuse a liquid into the solid, you go backwards, of course, that's going to have to be exothermic. Heat's going to have to be released by liquid water to freeze out, and vice versa. To vaporize a substance into a liquid, heat's going to have to be given off in that process as well. There's an analogy here to some of the later topics of calorimetry. Maybe we'll talk about this in class on Friday. We'll see. The issue here is, imagine you're working out and you're sweating, and so you have liquid water on your skin. And the idea here, and you probably know this, is that you're not supposed to wipe the sweat off because it's supposed to evaporate. As that water evaporates off you, the evaporation process is the liquid to gas. That's an endothermic reaction. Okay, we talked a little bit about if reactions should heat up their surroundings or cool down the surroundings. Let's think about this endothermic reaction taking place on your skin. So as water is evaporating off your skin, the water molecules have to absorb heat in the process in order for that process to occur. So you are losing heat as water evaporates from your skin. And so since you lose heat, your Q is dropping. So the heat of the surroundings is dropping as this reaction takes place, as the reaction has to absorb heat in order to occur. So the reaction's absorbing heat in order to take place, and then that leads the surroundings to lose heat. So you have this inverse relationship between the surroundings and the reaction. So you feel cooler. So you feel cooler because that's an endothermic reaction. The reaction is only accomplished by water absorbing energy, making you feel cooler in the process. So let's use that to get into this coffee cup calorimetry problem, because the whole idea of calorimetry stems from, let's have a reaction take place in some sort of a medium where we can track the temperature of the surroundings and then relate that heat change of the surroundings to the reaction's heat change. So the key idea behind almost any calorimetry problem is that the heat change that the reaction undergoes is the negative of the heat change of the surroundings. Now sometimes I write this expression and people start thinking, okay, Q reaction has to be positive, Q surroundings is negative. That is not what this equation means. This equation just means whatever the heat change is for the reaction, the surroundings has the opposite heat change. So if the reaction is absorbing heat and the Q of the reaction is going up, then the surroundings is losing heat. And then likewise, if the reaction is releasing energy, then the energy has to go somewhere. It's going to the surroundings to warm them up. So you get this inverse relationship that if there's a drop in heat of the reaction, there's a gain in the heat, i.e. the temperature of the surroundings. And if the reaction is the other type, where it's absorbing heat, then the heat's dropping in the surroundings. So this example here says that calcium oxide reacts with water to yield calcium hydroxide. Write the balanced reaction. That's not too hard, so let's write that out. Whoops, why did I click the wrong button on my screen? Okay, so we're going to have calcium oxide. I don't want green. I don't know why it matters. Let's go to this. Calcium oxide is being added to water to form, we probably need water as a reactant. And we form calcium hydroxide. Calcium hydroxide is water soluble, so of course it's going to ionize in the process, but our reaction is balanced. 2 H's, 2 O's, and a calcium. Okay, we're putting 5.40 grams of calcium oxide into 500 milliliters of water. We're given a density. Assume the specific heat of the solution is that of water. The temperature of the solution is observed to change to 27.60 degrees C. Notice that the original temperature of that solution was 25.00. So delta T here is 2.60 degrees C. Always T final minus T initial. So you get the sign right. So the temperature is going up, positive 2.60 degrees C. Is this reaction exothermic or endothermic? Okay, the big thing here is when the temperature goes up, it's not the temperature of the reaction, it's the temperature of the surroundings. The temperature of the surroundings is going up, means that the reaction is losing heat. The reaction is exothermic. So the delta H of this reaction should be negative. Okay, if we calculate anything other than a negative delta H, we've probably made a mistake. Now, the way we can go about solving a problem in an example like this is to imagine what the surroundings is. What is the surroundings of this chemical reaction? The surroundings is really just this water that the reaction is taking place in, that we're seeing the temperature change in. So we can write that or recognize that the surroundings is just the solution that the system resides in. So this we could express our Q reaction is just the negative Q of the solution. Now the solution is mostly water. Water is a pure substance. We like to describe pure substance with a specific heat. We have a specific heat given here, joules per gram Kelvin. So our solution can be described by that MCS and the delta T, and these all being for the solution. So the mass of the solution is everything. So it's the mass of the solution here is going to be the mass of water. A lot of problems will just give us the mass of water here instead of the volume, even though it's easier in the lab to measure the volume. So this example here just needs us to consider the density of water. So we have 500 mils. Where the heck's my calculator? I don't know where my calculator is, but so 500 milliliters of water. We just want to know the number of grams, so we'll take the 500 milliliters. And then take the density, multiply by 0.9970 grams per ml. The volume cancels. And so that'll be 500 times 0.9970 for 498.5 grams. Okay, so the mass of the solution is going to be the 5.40 added to that. So that'll be 503.9 grams. So this should be 503.9 grams. The CS of the solution, 4.184 joules per gram Kelvin. And then the delta T is 2.60 degrees C. So the degree C does cancel with the Kelvin. Remember, this is a delta T. If you don't think it cancels, convert both temperatures to Kelvin, then take your difference. It still works out to be 2.60 Kelvin. Said that a few times. Hopefully that sinks in. And we got to keep this minus sign. We got to plug in the actual temperature, the delta T, in its right sign, which is positive. So I get my Q reaction here to be equal to 503.9 times 4.184 times 2.60. The negative of that, so this is minus 5,482 joules. Now, let's see what the question is asking for. This is probably the most crucial part of the problem. See what's being asked for. What is the standard enthalpy of reaction in kJs? They want the standard enthalpy of reaction of this reaction here. So the standard enthalpy of that reaction would be the enthalpy of 1 mole of calcium oxide reacting. This is not 1 mole. 5.40 moles of calcium oxide is not 1 mole of calcium oxide. If it was, then this would be the answer to the question. But obviously that's not 1 mole. So what we need to do here to get delta H of that balanced reaction is we need to take the energy released by this particular reaction, which was 5,482 joules. Let's write that as kilojoules. That's really easy, right? 5.482 kJs. If we're tracking sig figs here, we got 3 sig figs on our temperature. We're doing multiplication, so we're going to be over here at the 5.48. Okay, now this is the heat that's being released specifically by this amount of calcium oxide reacting. Just imagine how this would change if we had more calcium oxide present. We would have seen a greater energy change because more reaction would have been occurring. And the magnitude of the Q reaction in delta H is dependent on the quantity of the reaction. It's the extensive property of the substance. An extensive property of the substance. So the ratio here, we can think of this as a ratio. This is the heat per gram, per 5.40 grams. So I want to divide by here. The substance I want to choose to divide by is whatever limits the reaction. So I just want to find the limiting reactant. In this case, it's really easy because there's only one. I mean, there's 2 reactants, but there's a lot of water. I don't think you're going to be too worried about solving a limiting reactant problem, right? We definitely can see that water is the excess reactant in this reaction. But if we have multiple reactants and we're not sure, we just have to go through a limiting reactant problem like in chapter 3 to identify which substance is the limiting reactant. And then if this is per mole, like so the delta H of the reaction means 1 mole of calcium oxide reacting with 1 mole of water to form 1 mole of calcium hydroxide, then we just got to go to moles. So it's going to be 16 plus 40.08 grams for calcium. That's 56.08 grams per mole of CaO. And then the reaction has 1 mole of CaO in it, because that delta H of a reaction should just be units of energy. So that's how we get rid of the mole. It's just by looking for the moles of calcium oxide, just one in the reaction, so that gets rid of the moles. So we're saying minus 5.482 kJs per gram per 5.40 grams of calcium oxide is the heat released by the reaction. We just convert grams over to moles and then multiply by moles. And so if we carry this problem out, this is going to be (56.9). So negative still, 56.9 kJs is the delta H of that reaction. Now think about doubling the coefficients. What happens if we double the coefficients and just randomly said, okay, well, what if we had this reaction instead? We had 2 here, 2 here, and 2 here. How would the delta H be solved accordingly? Well, this one would have been a 2. And then this would have came out double the magnitude. And just like you could have known, if you take a delta H of a reaction, then you double all the coefficients, you double the magnitude of delta H. So hopefully that's reinforcing of how we can manipulate reactions and then how we might solve and determine the delta H from a balanced reaction using a calorimeter type problem like this one. So the Baum calorimeter is this constant volume system. So you have a closed, let's choose a different color, a closed container. So we have a closed system enclosing a combustion reaction. So generally what happens is you have this container sealed with O2 gas and a lot of it. So that's the excess reactant. And then you have some organic compound that can combust. So you have something that combusts. So some sort of a compound. So this is a cell that is not filled with water. It's just surrounded by water. The outer chamber is surrounded by water. So when the reaction takes place, it's going to heat up the surroundings so that the temperature of the water should increase. And then you can track that temperature by using a thermometer. Okay, so you can see the change of the temperature before and after the reaction. The only main difference here between this form, well, the two main differences of this form of calorimetry and coffee cup calorimetry is this is now constant volume instead of constant pressure calorimetry. But the other change is that all of this stuff here is usually fairly expensive and reusable. So what you might do for this form of calorimetry is come up with one term, like one heat capacity for this entire object, and then relate that heat capacity times delta T to come up with the heat of the calorimeter. So you can use a heat capacity. This is best described when you have an object that doesn't have, you can't easily think of the mass of the substance because there's a lot of different substances here. You got the whatever surrounds the water, you got the stirring motor, you got this container, whatever it is, but all of these pieces are reusable. So you generally find and standardize one term, a heat capacity of the calorimeter, and all you need to do is multiply that by the temperature change of the calorimeter, the temperature change of the water. Let's take a look at a problem. So this problem here says we have a 4.0000 gram sample of methyl hydrazine with the formula shown. It's a rocket fuel, so we should readily know that energy is definitely coming off of this reaction. This is going to be an exothermic reaction for sure. The nature of Baum calorimeters is that almost always they're going to study exothermic reactions. I think it would just take a weird example to do an endothermic reaction. So you can almost think of every example in this form of problem is going to be releasing heat to the surroundings. So we have this sample combusting in the calorimeter, has a known heat capacity 7.7940 kJs per Kelvin. And this includes the water that's insulating the Baum. The one part that I can see you guys maybe getting a little bit confused by is you have this water in this calorimeter that surrounds it. What you would have to have is a very precise delivery system. So every time you repeat the experiment, you dry everything out, and then you add the exact same amount of water each and every time. So that's also part of the sort of system that's standardized and very controllable. And so upon combustion, the calorimeter Originally at 25 degrees, warms up to 39.5 degrees. What is the enthalpy of combustion per mole of the substance, and what is the delta H of that balance reaction above? These are the two main types of questions that you expect to find in a bomb calorimetry problem. Enthalpy of combustion per mole of substance. Sometimes maybe per grams of substance is like relatively fine to ask too. And then also, what is the delta H of the balance reaction? So let's come back to just a very simple equation. Sometimes students wonder, like, what's the best starting point? Well, we want to know the heat change of the reaction. If we knew that, we can probably figure out the answer to the question. It's always the negatives of the surroundings. So the negative Q of the surroundings, the heat of the surroundings is equal, the negative heat of the surroundings is equal to the heat change of the reaction. So again, reaction here is going to lose heat as it's releasing that heat to the surroundings. So the temperature of the surroundings should be going up during this type of reaction. Now the surroundings here is just the calorimeter instead of a solution. So the best way to describe the surroundings of this reaction is with the entire calorimeter system. So you get one term, Qcal, and then that Qcal is an object with the heat capacity shown here. And so we just write minus Ccal times delta T. Okay, now we're just keeping this minus sign because of that relationship between the calorimeter's heat is the surroundings, so it's the negative of its heat is equal to the reaction's heat change. So all we have to do to find Q reaction is take the negative of the 7.7940 kJs per Kelvin and then multiply that by the delta T, final minus initial. So in this case here, that's 14.500 degrees C. Okay, so that works out to be 7.794 times 14.500. I did my math wrong. Let me do it again. 7.7940 times 14.5, negative 113. And it's already in kJs. And we could get two more digits, so let's be more accurate. Minus 113.01 kJs, because all 5 digits there should be significant. Okay, now that's just not the answer to the question, though. That's just the heat change by this reaction of 4 grams of methyl hydrazine in this particular calorimeter. So now to find the delta H of combustion, well, we know that we get minus 113.01 kJs whenever we combust 4 grams of our sample. And so if we wanted the kJs per gram enthalpy of combustion, the enthalpy of combustion per gram, we could just divide 113 by 4. But that's not what we want. We want the enthalpy of combustion per mole. And so, again, we would look for the limiting reactant here. And the limiting reactant being that organic substance. The oxygen in the calorimeter is always going to be in excess. So this oxygen gas is always in excess here. So we're using the 4 grams of the methyl hydrazine. Methyl hydrazine, let's see here. We have a carbon, 12.01. We have 2 nitrogens. And we have 1, 2, 3, 6 hydrogens. So that's 46.08 grams. So 4 grams of methyl hydrazine, converting over to moles of methyl hydrazine. Now, we could stop here and calculate. That'll give us our delta HC. So let's write that down here. So do 113.01 negative, divide by 4 times 46.08. Gives us a enthalpy of combustion of 1301.9. It's still negative. kJs per mole. And then if we want the delta H of the reaction, notice that there's 2 moles of methyl hydrazine. So all we have to do is say, well, there's 2 moles of methyl hydrazine. The enthalpy of combustion is minus 1301.9 kJs per mole, 2 moles combusting. Just multiply by the 2 moles of methyl hydrazine from the balance reaction. So just double that to minus 2603.8 kJs. Okay, so that's a bomb calorimeter example, and it's In some ways simpler, but only if you understand why it is that it simplifies down this way, that the surrounding is just the entire calorimeter, and then we replace that object's calorimeter, just use the delta T of the system to work out the heat change of the reaction. So the mistake in this problem sometimes is looking for some mass term, so sometimes we get confused by Q is equal to MCS delta T. This works whenever we have a specific heat in mostly a pure substance, but a calorimeter here, this is really not a pure substance, this is a bunch of stuff. This is the case where we have an object with a C-cal times delta T to relate to that heat change. Good news, there's usually not a lot of variability in these problems. The only thing you might vary is we could tell you the enthalpy of combustion or the enthalpy of a reaction in units kJs per mole or reactions delta H, and then you can use that to see how much heat the reaction's releasing, and then use that to solve with a C-cal to find delta T, or you can use that with a delta T to find C-cal. So that's really the only variation in these problems is, do we give you Q reaction and you solve for C-cal or delta T, or do we give you C-cal and delta T and then you go find Q reaction and then ultimately solve the particular question at hand? So Hess's law is just the idea that we can take reactions, manipulate them, add them together. So we can take these two reactions, the water liquid is on both sides, so if we add these up, the liquid water is going to cancel out. So we have two liquid waters on the left side, two liquid waters on the right. Whatever their enthalpy is on the left side balances it out on the right side. So our overall balanced reaction would be CH4 gas plus 2O2 gas goes to CO2 gas plus 2 H2O liquid. And then delta H here would be the sum of these two delta H's added together. So minus 890 plus 88 will go to minus 802 kJs. So the key, though, is maybe we could be given a reaction that looks like this one, and then maybe we would be given water gas to water liquid. Delta H is minus 44. So if we're given this reaction here, maybe we'd have to take this, flip it, and then double the coefficients in order to cancel out appropriately. So Hess's law usually involves giving you 2, 3, 4 reactions that you have to manipulate to add up to some fourth or fifth reaction. But the key is you got to find, do you need to flip the reaction? You need to double the coefficients. You got to keep it the same. How do you need to change the reaction? And how do you adjust the delta H accordingly so you can then add the reactions up and then add up those then corrected or changed delta H's? Enthalpy of formation is defined as the energy change for the reaction in which a compound is made from its elements in their most stable elemental forms at room temperature. Only mildly confusing part here is, well, what are these elemental forms at room temperature for all the elements? Well, for most of the elements, you can get an appreciation for, metals generally being the metal solid, with the exception of mercury being a liquid. You have a lot of diatomic molecules, in particular with gases, but not exclusively with gases. So you have like O2, you have N2, you have F2 existing as a gas, Cl2. These are all gases at room temperature. You then have bromine, which is a liquid, I2, which is a solid, carbon, which is a solid in graphite form. And that's probably the extent that I would expect you to recognize that these substances in those particular states, physical states, have zero enthalpies of formation. And then everything else would have a non-zero delta HF, or would have some enthalpy of formation that is just the energy it takes to form that substance from the elements in their standard states. So if you're talking about the carbon monoxides, delta HF, you'd be making carbon monoxide. You can make it as a solid liquid as well, because those would have different delta HFs, but let's talk about its most common state of forming it in the gas. The delta HF, the enthalpy of formation of CO would correspond to the reaction where we make a mole of CO from carbon solid graphite form and then oxygen in its form of O2 gas. So we'd have to take half an O2. This is the one equation where it's actually legal and perfectly valid to leave fractions in the reactants, because we're always making 1 mole of the substance in the product side, so that the delta H of this reaction, whatever it is, just corresponds to the delta HF of CO, and then we would usually report that in terms of the number of kJs per that 1 mole. So usually you think of delta HFs as being units of energy per mole, and then the combustion reaction forming 1 mole so that the reaction has the delta H for just 1 mole of the substance reacting. So then the delta H's can be of F, the enthalpies of formation can be used to calculate enthalpies of reaction. So the utility here is that you can look up values for the products and subtract them from the reactants to determine the delta H's of reactions. So it's pretty useful for determining delta H's of reaction. So this here shows a chart of a variety of different substances. The chart is showing acetylene and ammonia, benzene. Many compounds, though not all, have negative delta HFs, implying that the compounds that we form are generally more stable than their constituent elements. That's usually why the compound forms in the first place, as opposed to just reacting back to the elements. But you also see that there are some compounds that are not zero. You see diamond has a positive delta HF, so that is a lesser stable allotrope of carbon. We saw in lecture that ozone was a lesser stable allotrope of oxygen. But you see here some delta HFs. Carbon monoxide minus 110 kJs per mole is the delta HF of CO. So then the utility here is to take and solve for the delta H by just taking 3 moles times CO2s plus 4 moles of water and then minus 1 mole times propane. Oxygen we should recognize as 0. Usually we wouldn't tell you this is 0, say on a test or a quiz problem. We would just expect you to remember, okay, the delta HF of oxygen is equal to 0. Okay, now I'm going to go through a somewhat painstaking effort to show you why this works. I don't know if this is needed because this is such a relatively easy to use topic and method. I don't know if you really need this, but imagine, let's start with the products that you write out the delta HF reaction. So imagine you take CO2 and you form CO2 from carbon, graphite. Let's just call it solid. I'm not going to write graphite in. So let's just call it carbon solid. We know it's graphite. And then plus O2 gas. Okay, and then we need to recognize that the delta H of this reaction would correspond to the delta HF of CO2 times a mole. So this should just be given by the delta HF of CO2. And so then we're going to have to multiply this, though, by 3 in order to get the right number of CO2s, right? So we're going to need to multiply all of these coefficients by 3. Okay, so then we do this for water. Let me not forget to write in the physical states of the substances. So water liquid comes from H2 gas reacting with half an O2 gas. And the delta H, this gives us the delta HF of water. Now we're going to have to take this reaction and quadruple it to get 4 water. So we could quadruple this reaction. So 4H2 makes 4 waters. So 4 times a half is 2. Okay, fair enough. And so then let's take propane and recognize that we want propane on this side here. So if propane reacts, it's going to go to 3 carbon solid plus 4H2 gas. Another way of thinking this is the elements that would form propane are carbon solid and 4H2. So what I've done here for propane is I flipped the reaction. So I made this the negative delta HF of C3H8. And C3H8 here, this would be for it in the gas phase. Okay, now if I were to add these reactions up, do you see what happens? If I try to add these reactions up, my carbon solid is canceling. My hydrogen's canceling. The O2s add together give me the 5 O2s. So those magically add up to the right number. It's really not magic, though. It's chemistry. So we get 5 O2s. And then 3 CO2s plus 4 waters. So the reason why this works is when you have a balanced reaction that's properly balanced, you have the products coming from the same set of elements as the reactants come from the same set of elements. So they're both coming from the same set of elements. So if you're referencing the enthalpies of CO2, water, and C3H8 off of their elements, all you need to do is take the products minus the reactants. So in this case, the products, 3 times CO2's delta HF, 4 times water's delta HF in the liquid phase, and then minus the 1 mole times the C3H8 delta HF. And water, or the oxygen you can see here, doesn't matter in this particular problem because O2 is already in the elemental form. So we didn't need to worry about O2, what it comes from, because it would come from itself, and we simply didn't need to even bother considering that particular reaction. So that's basically a Hess's Law picture for why delta HFs work the way they do. Now, it's not that hard to also just know that you just take the sum of the products minus the sum of the reactants with the delta HFs to find the delta H of the reaction. And this is exact. So when you solve your delta H this way for your reaction, this is the exact reaction of delta H. This isn't like an approximation. This should be like the exact value you should expect to find or measure in the laboratory for that particular reaction. So then basically for delta H, we're just using Hess's Law. So N and M are stoichiometric factors, so you have to factor in the stoichiometry of the reaction to sort of keep Hess's Law functioning in the proper way. Then we were talking about bond enthalpy. Bond enthalpy is associated with the energy it takes to break a bond. Breaking bonds is always endothermic. So the breaking of bonds always has an endothermic nature to that reaction. The molecule of, say, methane always has to absorb energy to break its bonds. Now, once you imagine methane breaking its bonds and they make some new bonds, maybe those new bonds are going to release more energy than it took to break those bonds in the first place. So the question when a reaction occurs is kind of, do the new bonds in the products become more stable or less stable than in the reactants? The bond enthalpy problem allows us to get a glimpse into that particular question. So bond enthalpy is always positive because energy is required to break chemical bonds. Energy is always released when a bond forms between gaseous fragments. So if we're taking like two H's together, forming H2, energy is always being released when we make that new bond. So the greater the bond enthalpy, the stronger the bond. So some bonds have bond enthalpies in the order of 500 to 1,000 kJs per mole. Those are very strong bonds. Weak bonds have bond strengths around 100 or 200 kJs per mole. So the idea of a bond enthalpy chart we'll see one, I think it's on the next slide, is that we can add up all the energy it might take to break the bonds in the reactants. And again, that should be an endothermic process. Then we can subtract the energy we get back when we make all the bonds in the products, those being representative of our new bonds. And then the result, though, is just an estimate of the delta H, and not always an exact delta H of that reaction. So here, the only weird thing is you're taking the sum of the broken bonds in the reactants minus the sum of the formed bonds in the products. So that's the only kind of peculiar thing here, is that for this delta, you're doing a reactants minus products, which might seem strange, but we'll demonstrate why that works perhaps on the next slide. So the reason why this works, if we're picturing the reaction, say, of a CH bond and methane breaking and a Cl2 bond breaking, we're actually going to leave these three CH bonds here intact and not break those ones. We're going to leave those there. And then we take those broken bonds, so we'd have to break one CH, one Cl2 bond. Energy is going to have to be absorbed through that process for that to occur. Then we're going to get energy back when we make the new bonds. The new bonds being, what if we mix a carbon and the chlorine together, make a CCl bond, and then we make an HCl bond as the other particular bond. Now what really matters is when you have 413 for the energy it takes to break the mole, 1 mole of CH bonds. So that's the bond H energy for the CH bond from the bond enthalpy chart. Without looking, I think Cl2's is 242. Let me pull up a bond enthalpy chart somewhere else. It's in the notes. I'm going to hit pause for a second. Yeah, and so to break the Cl2 bond takes 242 kJs. So that's 413 plus 242 to break the two bonds. And then what we're getting back is the carbon-chlorine bond strength. That's 328 kJs. And then we're getting the HCl bond strength back, and that is 431. So it's going to take 413 plus 242 to break the two bonds. That's 655 kJs. Then we make the new bonds. We're getting this bond strength back 759 kJs. So the energy it takes to break the bonds, you can think of that as being, okay, if we're going from CH4 plus Cl2 using Hess's law to CH3 plus H plus Cl plus Cl, that delta H is equal to the bond strengths that we use here to break the bonds. That's 655. Then we make the new bonds. We take our CH3 fragment plus H plus Cl plus Cl, and then we make CH3Cl plus HCl, our new bonds. The delta H for this step is minus 759 kJs. So applying Hess's law, we add these up to calculate the overall balance reaction for CH4 plus Cl2 going to CH3Cl plus HCl. The delta H there would be minus 104. For an exothermic reaction. But the key here is you can see that the exothermic reaction, this reaction is exothermic because the newly formed bonds are stronger than the bonds that had to be broken to make those new bonds. So the new bonds in the products in this reaction are stronger than the reactants bonds, leading to that negative delta H. Now, if we find we have an endothermic reaction from this process, then what we would conclude is that the products bonds in that case are then weaker. So if we were to break the bonds in our products here, it would take 759 kJs per mole of energy. That's more energy. It takes less energy to break the bonds in the reactants. That means the reactants bonds are weaker. The products bonds here are stronger. Okay, so we've mostly come to the end of the chapter, so we can maybe review some of the learning objectives of some of the things you want to make sure you can do at the end of the chapter. We want to describe the potential energy that can accompany the formation of making and breaking chemical bonds. We were just talking about this here, that if we're making a bond, that energy is being released. If we break a bond, energy has to be absorbed. Okay, and the same thing, we talked about this in the beginning of the chapter, not in this video, but we're talking about ions, that if you have two ions brought together of opposite charge, it's going to take energy to separate them. Just like if you brought the ions together, energy would be released. And if you tried to bring together two positively charged cations, energy would be increased through bringing two like-charged ions together. We want to distinguish between the system and the surroundings in thermodynamics. I think we find this example to be the main objective that we're sort of using behind a lot of those calorimetry problems. So if you're getting stuck in a calorimetry problem, maybe we need to review system and surroundings and think of open versus closed systems, and then the system from the surroundings. The system is the reaction. The surroundings is what that reaction is in contact with. Calculate the internal energy from heat and work and state the sign conventions of these quantities. I think it's going to be more useful for us to not do math problems of giving you random values of heat and work and have you calculate delta E. That's pretty boring. I think what's more useful is just thinking about different types of reactions where we can consider the sign conventions of W, heat, and delta E. Like I said, for some reactions, this is easier than others to understand the relative signs of these particular values. Sometimes you have to know how the reaction is being carried out. But you can also look at the gas being absorbed by the reaction or being released by the reaction and the type of system it's occurring in to get a sense of the sign of W as well for the reaction. We talked a fair bit about that in class. We want to explain the concept of state functions. So that is a path-independent function. Non-state functions are sometimes called path functions. So that's like heat and work are the path functions. Delta E and delta H are the state functions. Calculate delta H from delta E and P delta V. I don't think we really need to worry about doing math problems with these examples, but more thinking perhaps at how we derive delta H, or just understanding that delta H is exactly equal to heat change at constant pressure, because the constant pressure system is either considered to not do work or that its work is being canceled out naturally from the way we can write delta E and delta H's expressions. So we can relate the heat change at constant pressure to delta H and indicate how the signs go for these two values to predict exothermic versus endothermic. So like a Q negative for a reaction is an exothermic reaction. The reaction releases enthalpy or heat. And delta H positive, reactions absorbing heat as it occurs. We want to use thermochemical equations to relate the amount of heat energy transferred in reactions at constant pressure to the substance involved in the reaction. That's basically our coffee cup calorimetry problems, or even the case where you're just sticking hot metal into cold water and calculating temperature changes or considering temperature changes. We want to calculate the heat transferred in a process from temperature measurements with heat capacities or specific heat. So these are our calorimetry problems. We want to use Hess's law to calculate delta H's. Use standard enthalpies of reaction to find enthalpies of reaction, or vice versa. We could give you, maybe a delta H of reaction and all but one of the reactant and products delta HFs, and you can solve for that delta HF. You can use average bond enthalpies to then estimate reaction enthalpies, like we were doing at the end of this video. Some of the key equations: work is force times distance, electrostatic attraction equation, just relating the magnitude of charge. So as the charged particles increase in charge and they get closer together, the better for the energy of electrostatic attraction. So the further ions are away, the less attracted they are, the closer they are, the better. Delta E is just E final minus initial. Delta E is heat plus W. So the energy change for a system is just whatever the heat change is plus whatever the W change is for the system. Enthalpy is just defined as energy plus PV. So we found delta H is equal to QP just by doing some rearrangements. I don't know if I'd worry about showing the derivation, but just understanding where we get the idea that delta H is equal to QP for the systems at constant pressure. Work is related to the pressure volume work. I don't know if I necessarily worry about memorizing that equation, but just helping understand that when reactions are pushing maybe a piston because they're generating a gas, then the sign of W is negative, and then if the piston is working on that system, a gas is being absorbed by the reaction, then the opposite would be true, and the system is working on the surroundings. So this would be W greater than 0. The piston moving outward would be work being done by the system. Work sign would be negative in that case. And then here's the quick little derivation of delta H into the QP. Q is equal to MCS delta T, relating specific heat to mass and delta T. You can also write that Q is equal to CCal CCal times delta T whenever you're just talking about an object's heat capacity. So this would be just using the object's heat capacity in units of kJs per Kelvin or degree C, and just multiplying by the delta T. Q reaction is negative CCal times delta T. This is our main equation we're using in the bomb calorimeter problems. Products minus reactants for delta H, and then bonds broken and reactants minus bonds formed in products for approximation of delta H using the bond strength approach. So now there's just one last problem that I thought, or two kind of linked problems that I would recommend that you give a try. Hopefully most of the problems you see in a video like this, you actually go ahead and hit pause, give them a try, and then you can watch the solution. These ones I'm going to go ahead and just basically stop the video, work these out, then hit play and quickly summarize the particular results. Okay, so the heat it takes to warm up a liter of water, just assume 1.00 grams per ml. Nothing fancy with the density there. To assume you have a kilogram of water or 1,000 grams, and then MCS delta T, so delta T is 75 degrees C times CS and 1,000 grams. So that's 314 kilojoules, just the 2 sig figs. So then methane's burning with oxygen to make CO2 and water. Delta H of that reaction is minus 888 kJs because we have 1 mole of CH4 combusting. So I know that I need the reaction to give off 314 kJ. So I need the reaction to lose 314 kJs. So I keep the minus sign, and I keep the minus sign, the 888, because I want the reaction to lose this amount of heat in order for there to be enough heat to heat up the water. And so then that's 888 kilojoules per mole of CH4, and then a mole of CH4 with its molar mass over to grams. So I got 5.7 grams of CH4. All right, thanks for the attention. That's all for the video.